Good afternoon, everybody. Welcome to Open Classroom. I'm Janet Gillow, the Director of Professional Development for the Brown School here at Washington University in St. Louis. Glad to have you with us for today's program. I'm joined by my co-host and friend, Smriti Bajiracharya, who's the manager of our Masters of Public Health program and my co-host for the Artificial Intelligence and the Social Sciences series. For those of you joining on Zoom, you probably know this with the webinars by now, but we can't see or hear you and we can't call on raised hands, but there will be time in this program for your questions and your comments, and chat features enabled. So please do join in at every time that you have a thought that you want to throw into the mix. I want to extend a welcome to anybody joining on YouTube, either through the live stream or maybe watching this as a recording later. We're not able to moderate Q&A through YouTube and want to make you aware of that. So before I pass the microphone over, just want to let you know what we have coming up next week on Open Classroom. This is going to be our final week of the semester before taking a little bit of a hiatus. But on Tuesday, December 14th, we have a program from our Africa Speaks series. It's called Running with a Light Bulb, My Journey of Conquering Obstetric Fistula in Uganda. Brown School alum Alice Emesu is going to be speaking to us. And then on Thursday, December 16th, from our Inclusive Perspective series, we're going to have a talk on increasing employment opportunities for people with disabilities. Kimberly Lackey from Paraquat here in St. Louis is going to be joining. But now to start today's program, I'm pleased to pass the microphone over to Rupang Ann, who's Associate Professor at the Brown School and the leadership behind our Artificial Intelligence and the Social Sciences series. Rupang, please take us away.
Yeah, thank you so much, Janet and Smriti. So thank you all for your interest in our Open Classroom series on artificial intelligence and social sciences. The aim of the series is to introduce AI, machine learning, and deep learning to a diverse group of audience, discuss the applications of AI in big data analytics, assess the use and misuse of AI in social science research and practices, and also provide implications on the profound impact of AI, both positive and negative, on today's and future society. So we are invited distinguished speakers from various backgrounds, both academic and industry, and both social and natural science to speak about their unique encountering and adventure with AI. Today's talk marks our third one in the Open Classroom series. We are so fortunate to have Professor Liberty Vittert talking to us today. So Professor Vittert is a professor of data science at the Olin Business School at Washington University, and she is a graduate of MIT as well as the University of Glasgow. She is a regular TV and radio contributor to many news organizations, including the BBC, ITV, Channel 4, PBS, and FNC, as well as having her own TV series on STV. She is a regular opinion editorial contributor for the Fox News channel and has been featured in Popular Science, US News, Newsweek, Business Insider, International Business Times, CBS News, and The Conversation. As a Royal Statistical Society ambassador, BBC expert woman, and an elected member of the International Statistical Institute, Professor Vittert recently published a popular science book on data science titled 30 Seconds Data Science, the 50 Key Principles and Innovations in the Field of Data Gathering. So definitely check out the book on Amazon. She is also an associate editor for the Harvard Data Science Review and is on the board of USA for the UN Refugee Agency, as well as the HIVE, a UN Refugee Agency Data Initiative for Refugees. So although I only come to know Dr. Vittert recently, I'm really deeply impressed by her legendary career, her devotion to public education for data literacy, and her long-lasting passion for elevating international refugees. So without further ado, let's welcome Dr. Vittert to offer us her talk titled, What Do People Mean When They Say AI, ML, Big Data, or Data Science?
Thank you so much. I feel like Rupang, you should be my publicist. I was just saying that earlier, but now I'm convinced. It's so nice to be here, and thank you both for inviting me. I'm really excited to do this. These ideas and these slides and really the ideas were developed with me and a guy named Hans-Peter Pfister, who's a professor at Harvard. We co-taught a course, and it's because he's a computer scientist and I'm a statistician. And, all of these words get thrown around so much. Artificial intelligence, machine learning, deep learning, big data, I can't even take a breath. It's like, what are all of these things? And there's, you'll hear all the time, they used a machine learning algorithm, or they use artificial intelligence. Like, what does that even mean? And I think part of the problem is that there's a lot of different definitions, even between statisticians and computer scientists. So that's why Hans-Peter and I really came together to try to figure out a way to have a common language and a common fluency around all of this. So I'm going to talk for a little bit, and then we're going to look at some real interactive examples. And one of the reasons why I think it's so important to talk about AI in the social sciences, and ML, or whatever you want to call it, data science, is that it's so easy to become data-driven and to forget about the human side, to forget about the fact that every number is a real person, and that we are studying people, their actions, everything is in some sense human-driven, and that if you just look at the data, you can have some really enormous mistakes. And so that social sciences aspect is of the utmost importance to anything that we do in data science. So I'll sort of get started here, but I just want to do a general broad overview. And I want to take that word, the one word I want to take out of all of this is big data. People tend to use big data all the time. It's a catchphrase. But what does big data even mean? Is 100,000 points big data? Is 900,000 points big data? Is 10 million data points big data? Who knows? There's no official cutoff. 10 million data points means that it's big data, but 9.5 million isn't. There's no cutoff. So I just want to sort of throw out that word big data and just ignore it. And by the way, I have the chat open. So anytime anyone has a question during the talk, I'm more than happy to pause and answer. I think it's better to get questions as we go along. So I want to throw out big data, and I want to concentrate on data science, machine learning, and AI. So I will make the argument that data science is the overarching genre. Data science is what we should be calling anything we do with data analytics. Anytime we gather, collect, analyze, or interpret data, anything to do with data should be called data science. And then things fall underneath it. I would argue that artificial intelligence is bigger than AI. So if you all just agree with me and we say that, data science is the biggest thing, then we'll go on to the fact that we have these multiple genres, AI and ML. So what is AI? AI is where you create intelligent machines that can simulate human thinking, capability, and behavior. It's what we see in the movies. It's these intelligent machines that in some way simulate human thinking behavior. And then we also have our sort of machine learning, and that's where we use data and algorithms to make predictions and decisions. So actually, these machines, these autonomous systems, AI uses ML in order to simulate human thinking. So you can almost think of machine learning. It has separate uses besides just an AI, but AI uses machine learning in order to do it. If you're going to think if you're a robot and you need to think like a human, you're going to use machine learning in order to figure out how to think like a human. So you can almost think of ML as it falling under AI. In general, we have a couple different types. We have general AI. That's where autonomous things that are as intelligent as humans. That's what we see in the movies. We're not there yet. Okay, so don't be too worried. Maybe you're worried if we're going there, but we're not there yet. If it makes you feel any better, Boston Dynamics, if you've seen the thing where the robots are jumping around and dancing or whatever, if you show me a robot that actually does something useful, like deliver a pizza, okay, I might be worried. But right now, all they do is jump and dance around. That's not that helpful. So it's not that interesting, and they're really not simulating human behavior. And then we have something called narrow AI, which people are using a lot of. That would be chess playing. So they have a system that can play chess. It seems autonomous, but it's not. It's in this closed environment. You can't then go ask that machine to go play checkers. All it knows how to do is to win the game of chess. So it's in this closed environment. And then, we have this general machine learning, which is, anything we're using to do to predict, which is used in AI. And so there's a lot of overlap between AI and ML, but I would say that any AI uses ML, ML doesn't necessarily use AI. So let's start with machine learning. Let's start at the granular level and then go up. So we're here in machine learning. Sorry, I get too gesticulating when I'm talking. I just hit my microphone. We'll start with the granular of machine learning, then we get to AI, then we get to the overarching idea of data science. So what is machine learning? There's 3 different types of machine learning. The first is supervised learning. So that's where you make inferences and predictions from unseen data from labeled examples. So what does that really mean? What is a unlabeled example? Just to be clear, a label is where a human annotator, me, I go in and I label stuff. Cat, dog. I look at a zillion pictures of cat dogs and I label it. And then I create an algorithm that's going to figure out what makes a cat and what makes a dog from all those pictures that I've labeled. I put in a new picture and that machine tells me whether it's a cat or a dog. What would be a practical example of this? Housing prices. So Zillow, for example, is a supervised learning. Zillow has all of these tons of data of house prices. Just knows what zillions of things have been sold for. A new house comes in and it can predict what it's going to be sold for. So that's a supervised learning. Then there's something called unsupervised learning. That would be where you find data in things that haven't been labeled. So if you have 1,000 houses, you have no idea what they sell for, and this unsupervised learning system just sorts where the houses are, which one's more expensive, which one's less. It figures it out for you rather than we pre-labeled everything by having this selling price. You can also find new customer segments. So like if in business world or in the medical field, if you're trying to figure out what it is about somebody that means that they have a disease versus anybody else, you could put all of these people into an unsupervised learning and have it try to figure out by separating people and groups out on features what makes one person have a disease and one person not. And then finally, we have something called reinforcement learning. That you've done before. Netflix, it tells you what you're going to watch next. YouTube, you'll watch a video and then it'll pop up a new video that it thinks you want to watch. And it learns because if you decide after 10 seconds to click away from that video, it goes, oh, okay, that was a bad recommendation. I won't do that again. And it learns. But if you watch that video all the way through after it's suggested to you, it learns that, okay, that's something that you like or you don't like. So these are the 3 types of machine learning that we really think about: supervised, unsupervised, and reinforcement. Supervised, we're really good at. Okay, a human person goes in and annotates stuff. Unsupervised, we're not that good at yet. People are working on it, but it's not that great. And then reinforcement learning is getting enormous play because of YouTube or Netflix or anything like that. So let's just understand, what does it mean when someone says a machine learning algorithm? What is that? So here are the cat and the dog pictures that I put in that I talked to you about. So I've gone through and I have labeled, this is a cat, this is a dog, and this is a cat. Now I put that into this black box. But what have I done before? I've decided what features make a dog and make a cat. And I'm going to tell this algorithm what it is. So I say a cat has, pointy ears, a dog has, round ears, I don't know, whatever. I pick out the features that make a dog or cat, and we're going to talk about why that's really hard later. But I pick out those features and it goes into this black box, this machine learning system. system, and it learns what's a cat and a dog. So it'll test itself. It'll have created this process where it decides what's a cat and a dog, and then it brings in a picture where it technically knows the truth, but it's like putting your hand over the answer to the flashcard. You know what the answer is, it's there, but you're testing yourself before you pick up your hand to look at the back of the flashcard. So it'll test itself, and it'll get a dog or it'll get a cat, and it predicted that it was a dog, but it got a cat. It goes, oops, I screwed up there. I need to go back and figure out what I did wrong, and then try it again. And it just keeps doing that. It just keeps flashcarding itself. It's just your same idea as you memorizing something from flashcards and relearning. It just keeps testing itself. And when it finally decides, okay, I've gone through enough times and I know it, I don't have to look at my flashcard again, I know I'm going to get it right, it says it's done. And now I can take a new picture of a dog or a cat that I haven't labeled as dog or cat, and this black box, this machine learning system, knows and spits out whether it is a dog or whether it is a cat. But here's what's really hard. It's this data preparation. You know, people screw up. Think about how many times you've been making an Excel spreadsheet and you type in the wrong thing. Manually annotating things, humans are really not that good at it. There's always errors. And this is also where bias can be introduced, which we'll discuss later. But there are always issues, and it's really hard to do. But the system just keeps training itself until its predicted versus actual goes to zero. And that's what we call something called a loss function. And that's a fancy word, but I want to put in this terminology so that if it ever is in the back of your mind, it triggers it. But it's when that loss, how many times you lose, how many times you're wrong with the flashcard, you want to get that as small as possible for what you predicted to be the same as what the actual thing is. And then it tests itself over and over and over again. And just to go a tiny bit more granular about how it tests itself, it creates something called a random forest. And I promise this is as detailed as we're possibly going to get into this. But how is it testing itself? How is it deciding whether it's right with that flashcard or not? It's something called a random forest. So let's just look at our data here. We have ones and zeros. Ones and zeros, and I want to be able to separate out my ones and my zeros. So what are the features that I'm going to tell my machine learning algorithm to look at? I'm going to tell it to look at color and whether something's underlined or not. Those are the features of my data. So just like whether a dog has pointy ears or round ears, it's whether my ones and zeros are colored blue or red or underlined. So the first question it's going to ask itself is it red? So now it's separated two different sides. Our 4 zeros go one way, our 2 ones with our other 0 go the other way. Just like are the ears round or pointed? But there might be a dog that has a little bit pointy ears. I think it's corgis. Corgis have little pointy ears. So I have some corgis over with all my cats. So then it asks another question. It says, is it underlined or not? And that's where it separates it out. So with a corgi, I might say, is it over 10 pounds or not? And it's going to separate my cats and my corgis, just like it finally separates out my ones and my zeros. So this is how it goes through these features. And it's why what features you pick are so important. And what could have been a better feature here? Maybe shape. Curves versus straight lines. Although you see on the ones, they're sort of a little, I don't know if you want to say the little hat of the one is curved, I'm not sure. But how you pick those features is really important and really hard to how you separate out things. But what it'll do is it'll come up with a ton of different ways. So do you do the color first? Do you do the underlines first? Do you add in the curve detail? And it'll create a bunch of different types of these random forests, and it'll see which one gets it right the most. So what order of the features or what combination of these different features gets it right the most. And it'll do a bunch of these different things, and then it'll pick one, and it'll say this one's best or that one's best. So that's sort of as detailed as we're going to get into this granular level of what machine learning is. So just all over again, you have this human, they label a bunch of data, dogs or cats, they pick what the features are, they create this black box which tests itself over and over and over again using random forests. You're done, you've created your machine learning algorithm. I bring in a new picture of a cat and a dog, and it tells me which one is which. But it's actually really hard to do this feature engineering. So I'm going to ask you guys, there's 24 of us in here. There's not too many of us. We can do this. In the chat, what defines a cat? What defines those cats there? What's the feature? What would be one of the features that defines a cat versus a dog? What are the features of that cat? Can anyone write it in the chat for me? Ears, so pointy ears. Sound, they make them yes, and whiskers. Inconsiderate. I don't have a cat, so I'm not sure, but my dog would probably say that they're inconsiderate. Long, curvy tail, absolutely. Anything else? What else do they have? Mustache, the cute little mustache, yep. Maybe purrs, yep, the sound. Pink nose, absolutely. These are good. Under 40 pounds, very good. Fur, they have this cute fur. Is this still a cat though? Fur versus, uh-oh. Are you all seeing a red screen?
We're seeing a red screen.
Yeah, we saw the red screen.
That's weird. Let me try to reshare my screen. Zoom must be doing something weird. Sorry, everybody.
Yeah, no worries. Actually, yeah, there's probably something wrong with the system. Yeah. So, yeah, we can see it now.
You can see it now? Okay.
Yeah.
Weird.
Yeah, it's back.
Sorry about that. So, okay. So is that still a cat? So fur is a bad feature, right? That's a crummy feature. What about this dog? Those ears are pointy. We talked about pointy ears. We talked about, round eyes. I mean, I don't know. That cat, depends how open their eyes are, but absolutely, round eyes. What about the nose? Some of you all mentioned the little nose. A bunny nose looks just about the exact same as a cat nose. Just almost the exact same. And what about if you get something like this? I mean, I don't know. It has a bunny nose. I don't know whether that is a cat or a dog. So it's a lot harder than you think to distinguish the features, what features we're going to choose, whether we're going to make it a cat or a dog. Because fur doesn't work, nose doesn't work, ears doesn't work. It's really, really difficult to pick out those features. That's a very difficult part of this machine learning. And I wanted to just talk about how these features get figured out. In the last 10 years with machine learning, they've figured out new ways to do this feature learning. And it's where humans don't make a decision. So because it's hard for us to figure out what the features are that make a difference between a cat and a dog, and I keep using the example cat and a dog, but there's zillions of examples, but it's hard for us to figure out what makes the difference. There is something that has been created to help people do a better job with feature learning. And that is what deep learning is. Deep learning is simply saying, people, you are really bad at figuring out what the difference is between a dog and a cat and telling us what all these individual features should be. So instead, we're going to create something called deep learning that does it for you. So that's what deep learning really is. So what that looks like, it's very fancy, but the idea is that it goes in layers, okay? And what does that mean? It means that first, it has a high level of what's a feature that distinguishes someone. So let's say face. These are just general, like the first layer is sort of what you would look at. It's what our cortex recognizes. So the first layer is very much what our visual cortex, we know that first layer looks like faces. So faces versus anything else. Then the next layer is pieces of faces. So a person's nose versus their mouth versus their eyes. We can still what we see with our visual cortex, but it's separating them out. And then it goes to very, very low level features, the final layers, which would be stuff like the texture of your skin or a little scar or these sort of very much low level features that we don't necessarily even see with our eye. And once it looks at all of those layers to identify who someone is, it picks out this individual face. So deep learning, really the whole idea of it is deep learning is something to make feature engineering better because we're crummy at it. And then people spit out, and then it just goes to deeply. It just goes in a bunch of layers to figure out what an image really is. That's what deep learning is. So learns features automatically and has layered representations of what something might be. So then the final piece, and I promise this is the final sort of definition piece, is classification versus regression. So machine learning algorithms can do two things. They can either classify, it's just what you think, this is a cat and this is a dog. or it can predict, which is called regression. So it's predicting what something might be. So you have 1,000 houses and it's predicting what the price of a new house coming in. And that's different, right? It's not saying, is this a high price house or a low price house? It's saying, what is the actual price of this house? And that's the difference. So classification, you assign a label to an unlabeled example, cat or dog, whatever. So a label, just a little bit of definition, and I won't really go through this, but I just wanted to put it up in case you ever want to look back at it. A label is a member of a finite set of classes, so dog, cat. You can have 2 classes, you can have 3 classes. It could be dog, cat, fish, and it could be whatever you want. Versus regression, which is where you predict something. So think about it. Probably the best example is classifying things as low price houses or high price houses or medium price houses, or actually saying, I predict the price of this house to be $200,000. And I have sort of images that I think will probably help. So here's houses, and you could pick a zillion different features, okay? You could pick number of bedrooms, number of bathrooms, whether it's on a residential street, how far it is from a highway, whatever you want. But here we're just gonna pick this feature of square footage. So we have the house price and we have square footage. So here are our labels, our single family houses versus 2 family houses. What does classification do? It separates them out. We have single family houses versus 2 family houses based upon our features of the house price and the square footage. And classification says, here's a line that separates what makes 2 family houses and single family houses based upon our features of house price and square footage. What does regression do, which is another thing that machine learning can do the classification, or it can do this regression. So here we have our same single family and 2 family houses, but our label is now removed because we don't care. It's not like low price house, high price house, single family, double family, whatever it is. We want to bring in a new house, this new red house, and we want to predict what the price will be based upon these other houses. So based upon the house price and square footage, we want to know what the prediction will be, $450,000 based upon its square footage. So that's what regression does, is it predicts an individual number. Classification separates them out. But as we talked about, features are really important and really hard to figure out. So if I'm trying to figure out what's an apple and what's an orange, if my features are weight and roundness, I can't separate those out. I don't know how to separate those out. Weight and roundness, they're basically the same. There's nothing that separates them. But if instead I choose color and roundness, then I'm really able to separate out my apples and my oranges. So the features are really hard to figure out. And that's called feature engineering, which again is basically what's become deep learning. So self-driving cars, it picks features all the time. What features is it going to use to decide how to drive? Is it distance from an object? Is it speed of other objects? It uses tons of different features. Here you have, it's GPS, it's radar sensors, but which one does it trust more? What features does it use to make these autonomous learning decisions? It uses deep learning. It says people aren't very good at figuring out features, so we're going to use something called deep learning to pick out what to do. The jury is still out, as we've heard. We've heard of crashes and things that happen with Teslas all the time. I work on a show on Discovery Channel, and yesterday we were filming for it, and one of the videos was a Tesla was picking up people. They were in a cemetery, which makes it very creepy, but it was picking up people that you look out and they weren't there. And that means there's a problem with the feature engineering. It was recognizing actually a tombstone as a person. So the jury is still very much out on which features to choose. And there's different, for example, different car companies use different features. So Rivian uses different ones than Tesla. And it says that's one of their big proprietary things, is which features does it use. But as we talked about, feature engineering can cause some real problems. And you've maybe heard about this if you follow it at all, but there's been bias in a lot of these types of sort of AI or machine learning algorithms. So what does that mean? How do you create bias with these features? There was something called the Gender Shades Project out of MIT, and it was a really, really interesting study. If you want to Google it, this is all these images are taken from it. And it basically said, we think that there's a problem with facial recognition systems. We think there's bias in them. So they picked IBM, Microsoft, and Face++ facial recognition systems, and they decided to test them. They just picked 3 that are most used. Some are actually used by the police, and to try to see if there was bias in them. So what did they do? They picked 1,270 images. 1,270 images were chosen to create a benchmark for this gender classification test. So they picked subjects from 3 African countries and 3 European countries, and the subjects were then grouped by gender, skin type, and the intersection of gender and skin type. So how did these systems do? When you looked at them overall, so the overall accuracy on all 1,270 subjects, Microsoft got a 93.7, Face++ 90, IBM 87.9. That sounds pretty good. Like, they did a pretty darn good job. But what happens if we separate it out by the features of gender and skin type? So let's first look at gender. So if we simply look at how they did on female subjects versus male, and remember the overall is when you put these all together, but when we separate out by feature, which we've said is really hard to do, and we look at female and male, you start to see something interesting. It's always better on male subjects. So, I mean, really different. Look at Face++, 20% different, whether it's picking out male subjects or female subjects. I mean, really, really bad, okay? But now, so we know that the gender, and actually, my research is in facial shape analysis, so this is close to my heart. When you take away the social cues, hair, makeup, clothes, whatever, it can actually be very difficult to tell a man from a woman. I've seen it. When you're just looking at the face, it can be really hard to tell. And this Gender Shades project shows that the machines did a pretty bad job. What happens when we look at skin type? Darker subjects versus lighter subjects, we see the exact same thing. I mean, again, almost 20% difference in error rate on whether they're a light subject or a dark subject. That's huge. So we now know that it's really bad at both features that it's deciding on, gender and skin type. So what if we look at how it does on the 2 things combined, the intersection of gender and skin type? It is terrible. So when all 3 systems define a darker female versus what it's best at seeing, which is a lighter male, you're seeing error rates of 34.4%. That's enormous. It's only 65% accurate at looking at whether someone's a darker female. That's not that much better than flipping a coin. I mean, you have to remember 50-50 is what you get when you flip a coin. 65% isn't that much better. I mean, that's a huge difference. And that's really important to remember that 50-50 thing, because we hear 65, we compare it to 0. It's not 0, it's 50-50. It is terrible at this. So what this shows is that there are enormous amounts of error in these systems when you look at the individual features. It may sound like, oh, well, it's 95% accurate because it's so accurate when it's a lighter male that moves, it's like a weighted average. It makes it seem a lot more accurate than it is because it was 100% accurate whenever it looked at a lighter male. So what is the final idea? Error analysis reveals that 93.6% of the error of faces misgendered by Microsoft were those of darker subjects. 95.9% of all of the error happened when they were female subjects for Face++. So almost all of the error came from when it was determining if someone was a darker subject and someone was a lighter subject. And, if you look across the country, you'd be alarmed to see how law enforcement, how stores are all using facial recognition systems that are really bad, shockingly bad. People scan your faces all the time. It's 1 in 2, Georgetown, which does a lot of this work, estimated that 1 in 2 Americans have their face in some facial recognition system that's used by the police or stores right now. 1 in 2, half of you, half of the people in this room, your face is in some facial recognition system somewhere. And it's really poorly done. Why? Because there's enormous bias. First of all, most of the people that these systems are trained on tend to be lighter subjects, and a lot of them tend to be male. It's people who give their faces for this research, or old repositories that we have. And we also have our own internal bias. I'll give you an example. The research that I do, the faces that I work on, I can't take the data out of its secure storage facility. So during the pandemic, when I was trying to work on my algorithms to map the face, I look at mapping people's faces. I took a picture of my own face because I needed to work on my work, but I couldn't go into the office and use my data. So I put it on my computer, so I'm sitting at home. I worked on this algorithm for almost a month trying to map a face, and I was using mine. I was using my face. So I got this algorithm to be almost perfect. It mapped my face almost perfectly. So I took a picture of my fiance and I decided to try it and try his face in this system to see if it worked. And lo and behold, it was a disaster. His lips, it showed that his lips were where his eyebrows are and his eyebrows are where his cheek was. And shocker, the algorithm that worked so perfectly on my face did not work on an African American male's face. Shocking. But I didn't even think about it. I worked on this for a month. And I just I just didn't think about it. I was doing it in my own thing, looking at my face, and all of a sudden, shocker, it didn't work on his face. So we have our own internal biases of people who are creating these systems. So there's bias in all of these types of machine learning systems, whether it's about gender and skin type or anything else, apples and oranges, there can be issues with the data. Adrissa, you said any facial recognition governance? Not yet. Right now, the only type of governance is that some counties and some cities are banning facial recognition to be used with the police, but that's it, and it's just some of them. For example, I can't remember, I have the notes here. Reportedly, Baltimore Police Department scanned photos trying to identify people during the Freddie Gray protests. I wrote an article actually about a guy in Detroit. Police arrested him in front of his entire family and his daughters at his house because he was mistakenly identified as a thief. He'd never even been within 10 miles of the store that he reportedly stole from. He was kept in police custody for 30 hours, and it was all because of an error with a facial recognition system. So it happens all the time. So I just wanted to talk about where, these incredible issues that come with trying to pick out these features, which in turn make machine learning algorithms really bad. I also just wanted to show this one thing. It's called Teachable Machines. It's one of the coolest methods I've ever used to learn about machine learning. I use it with every class I ever teach. So I just wanted to show you what it is. It's so easy to do on your own if you're ever interested, or if you're in education to do it yourself. It's teachable. The link is here. So what is it? You create your own machine learning algorithm. It's so easy to do. I did mine. You can do image, you can do pose, or you can do sound. So let me show you what this looks like. So I wanted to do pose. Could it figure out what pose I'm in? So you just turn on your web camera and it takes a bunch of pictures. I did face forward, then I did my head turned to the left, and I did my hand up. And I wanted to know if it could figure that out. So you train the model so it creates that black box. It learns these. I've labeled it, right? This is a human annotator. I've labeled all of these pictures with my face forward. I've labeled all these pictures with my head turned left, and I've labeled all of these pictures with my hand up. It goes into the black box. It learns through whatever features it's deciding what the differences are. And then I can put in a new picture and it can tell me which one it is. So I put in, this is a new picture I took of myself, and it almost 100% predicted that my face was turned forward. Not that my head was turned to the left or my hand up, almost 100%. So it did a good job. So I did another one, and I turned my head left. And again, it 100% predicted that my head was turned left. And then I did another one with my hand up, it 100% predicted it. So it did it really well. But what if I try to trick it? I turned my head to the right, so it wasn't able to tell the difference between whether my head was turned to the right or the left. So clearly it was using features that weren't deciding directionality because it was wrong. My head was turned to the right. I put my hand up and I turned my head a little bit. It wasn't sure. Sorry, I put my face forward and I put my other hand up and it couldn't figure it out. Right now it was confused with my hand up and my face forward with the other hand. It didn't work. And what about when I put my head down? It got totally confused and didn't know what was happening. So then I decided to do another one. So I did my dog. So I decided to do, this is images. So I took 90 pictures of myself, labeled it Liberty. I took 94 pictures of Henry, the dog, labeled it Henry. I trained the algorithm. It decided whether features are different between Henry and I, and then I wanted to use it. So I put in a new picture of my face, and it 100% predicted that it was me. So then I put in a new picture of Henry, and it 100% predicted it was Henry. I put in another picture of Henry with a different background, and it again 100% predicted it was Henry. I did it one more time, and it again 100% predicted that it was Henry. So what if I try to trick it? So it did a really good job with distinguishing Henry and I. But what if I take a picture of myself with a black face mask on? All of a sudden, it has no idea whether it's me or whether it's Henry. So obviously, as soon as I put that black face mask on, it's not going to work, and it can't figure out who I am. So that's the other sort of important aspect of this, is someone can say, oh, I created this machine learning algorithm. It's really easy to trick it. Like, very easy. I put up my right hand instead of my left hand. I turn right instead of left. I put a face mask on, and all of a sudden, it can't tell me from my dog. So tons of different things use all of these features: robotics, imaging captioning, live video captioning, face recognition, obviously, object tracking, self-driving cars. We've talked already about how Tesla and self-driving cars are so many issues, and that there's crashes all of the time because of these incorrect types. So now that we've talked about, we've gone from data science, which is this overarching thing. We have AI, which are autonomous things that act like humans that use machine learning in order to do this. And we've gone into the granular aspects of machine learning. I want to take it back up to the general issues and problems you see with data science in general. So there's something called natural language processing. It does it all the time. So a chat bot, if you're typing into the box in a live, in a chat box, you're saying, my computer isn't working, or, whatever it is. I had to do Apple support for my AirPods recently, and I typed in, the left AirPod isn't working, and then it responds, oh, I'm so sorry that your left AirPod isn't working, blah, blah. That's natural language processing. It's from whatever you say, it picks up what things are saying. People do it with sentiment analysis a lot. So on Twitter, is someone angry or are they happy? Customers, if they type something, you want to know right away without someone having to look at it, is this customer angry or are they happy? So natural language processing is allowing some really creepy things to happen. There's a website called talktotransformer.com, and it actually generates text. So you input some text, and it will generate a paragraph of text based upon your input. So I tried it. I said, what is data science? And all of a sudden, it created this entire paragraph about what is data science. I've seen people use it for books before. So they're writing a new book, and they want to have some, it's always easier once you have a draft of something to write from it. People will use this stuff to write books. They'll start with, what is data science, or writing a book on data science, and then they'll go from this draft of natural language processing is created. And there's also enormous issues with fake news stories. So fake news stories are generated all of the time using this talk to transformer stuff. It scopes the internet for documents, and it actually creates fake news stories. The Wall Street Journal did an article on it. There's also lots of crime that happens with this. So fraudsters used this tech to mimic a CEO's voice. So it somehow got, here's the story. A UK energy company's chief executive was tricked into wiring 200,000 euros to a Hungarian supplier because he thought his boss was doing so. It mimicked the boss's voice and got this guy to wire money. How do we counteract or detect it? Think about any other business, healthcare, for example. Do you have cancer? Do you not have cancer? Looking at the radiologist images, there's lots of ideas about using image tech to be able to recognize that and not have a doctor actually look at it. There's tons of issues with that, voice recognition. Now, a lot of times people have tried to combat this, but every time they come up with a new way, the fraudsters come up with another way. It's like this cyclical cycle. Those annoying questions like where you have to identify the fire hydrants in the 9 pictures or something? That's trying to combat AI from logging people into things. But it's a enormous issue. Anyone recognize this person? Anyone recognize her? You shouldn't. She doesn't exist. So there's a website called thispersondoesnotexist.com, and it actually generates non-real people. So these are all not real people. They don't exist. It's just generating people and generate images that look completely real. So you can create fake people. You can also have people that you know do and say things. So let me actually stop sharing my screen, and I'm going to share this website. Stop share. 1 second. You'd think with the Zoom world I'd be faster at this than I am now, but you know, here we go. My students help me with this. So here's a CNN story. Can you all hear this?
During an era in which our enemies can make it look like anyone is saying
We have audio.
point in time.
That might look like President Obama addressing the nation, but it's not. It's actually actor and comedian Jordan Peele impersonating the former president, mixed with old video of Obama that was manipulated to match Peele's words. This is an example of what's known as a deepfake. It's a growing trend that's sweeping the internet. The technology can be used for some harmless fun, such as editing actor Nicolas Cage into movies he's never even starred in.
In my world, it means hope.
Well, here it's an S.
Yes, this is actually a thing. The technology can even be used to make people with no rhythm look like they can dance. But deepfake technology also has a dark side. Both private citizens and celebrities have seen their faces put without their permission onto existing pornographic videos, posing a new challenge for privacy issues. Appearing to say or do something one never did can also have political ramifications.
President Trump is a total and complete dick. Now, you see, I would never say these things, at least not in a public address, but someone else would. Someone like Jordan Peele.
It's easy to imagine how this can begin to cause problems.
So I want to try something with everybody here. Let's see if we can spot the deep fake. Let's see if we can do this. So, can you spot it? Let's just put it in the chat. When you're looking at the screen, is it the right or the left that's the deep fake? So as you look at the screen, is it the right that's the deep fake? So you put right in if you think right's the deep fake, left in if you think left's the deep fake. Which one is it? Right? Okay, we have some people saying right. Let's see. Correct. The people, this is the deep fake. This one here on the right is the deep fake. Let's try another one. Is the person on the right or the person on the left the deep fake? What do we all think in the chat? Okay, we think right. Let's try it. Correct. We were right. Everyone's so good at this. You guys are going to spot deep fakes all the time. The right is the deep fake. Let's try one. Let's try two more. What do we think? Right or left? Who's the deep fake? We have one vote for left. Left. Everyone thinks left. Let's try it. Correct. You guys are very good at this. We'll do one more. Who is the deep fake? Which Obama is the real and which one's the fake one? Right or left? Oh, we're divided. I'd say there's more lefts than rights, but some are saying left, some are saying right. No idea. I saw more lefts. Incorrect. The left one is wrong. It is the right one. And also, you're looking for it, right? You know one is right and one is wrong. But imagine if you just saw a clip of it without even thinking online, you'd be lost in a second. You'd have no idea whether it was a real person or not. So these deep fakes are getting really scary, and the feature engineering with these deep fakes. So really what I just wanted to show today, and I will wrap up, is that, this you sort of start with data science, you go to this world of AI and then machine learning, but machine learning, which is what builds it all up, has some real issues with it, with things that seem incredibly simple, like identifying a cat versus a dog. It's a lot harder than we think it is. And it creates enormous bias and enormous potential for really bad things. So thank you all so much for listening.
Thank you, Dr. Vittert. This was so great. And I love the examples, the real life examples that we use and see every day to, drive all of these points across. I was blown away in so many ways. So we are now entering the Q&A phase. So I can go ahead and get started. So my question is, I think my takeaway is that at this time, it's very easy to think about all the misuses or dangerous uses of AI and machine learning in the world. And it also feels like there is a big gap in literacy of what machine learning is and isn't. So I guess from your standpoint, where are we in terms of the progress that we should be making in terms of whether it's adding regulations, guidelines to improve so that machine learning is being used for better things than not.
Well, I really probably should have included one more example at this end of something where it's been used for good, because it's so easy to just look at all of the bad examples. So I will actually tell one thing that it's been used for good. We did a project with the UN Refugee Agency, UNHCR. There's a refugee camp in Kakuma, and it has over 200,000 people in it. It's been around for 30 years. So you actually have multiple generations growing up in this refugee camp. And people have obviously, it didn't start off for 200,000 people. It started off for about 1,000 people. So it's grown over time, and people build their own structures. A lot of things are made out of tents. And there's actually no map of the place. And that's sort of shocking to think. And it seems like it'd be easy to map something. It's actually very, very difficult to map something. That's a whole city, 200,000 people. So what did we do? And why do you need a map? You need to figure out where to put streetlights so girls can walk home safely from school. You need to figure out where to put new sanitation points. Where do you need more sanitation points? Without a map, you can't figure out how to do that. So we actually did a crowdsourcing, and we got satellite imagery donated of the camp, and we had human annotators. So at crowdsource, we just asked people to do it in their free time, and they would label on these satellite images where a structure was, because it was very easy to see structures, tents, or IKEA has these little structures, and would label it. We put it into a machine learning algorithm, and it mapped the entire camp by these structures. So there's also sort of incredible, and now we've done it with, I think, almost 100 refugee camps around the world. So there's incredible good that can come from this too. So I want to make sure that it's not just bad examples, and I should have put that one in there. And for my next talk, I will now do that to put in some good examples. But overall, in terms of regulation, the EU and the UK have done GDPR, which is their data privacy regulation. If you're involved in, a couple years ago, it was a huge pain in the neck, because if you work for a company that has offices in both, it was like this enormous nightmare for everybody for like a year to try to figure out how data was going to get across. But the US doesn't have anything like that. Which would be a wonderful thing if they did. So I think that the regulation would be sort of the key, the absolute key in this. We did a podcast recently with sort of a pro-government person and an anti-government person on this data stuff. One person who feels like the government's collecting way too much data, and one person who thinks the government should collect more. And the one thing they both agreed on, the only thing they both agreed on, is that the real enemy is big tech. And that's where the real danger comes from, is in how much data big tech is collecting on us. So I think government regulation is probably the only answer that everybody could agree on both sides.
This is just fascinating. I want to create some space to elevate some questions that are coming in from our audience. Ashley is really cutting to the heart of something by saying, so how can we advocate for more diversity or more accuracy in the development of facial recognition technology? You sort of referenced a really horrific situation of somebody being detained and terrified, probably because of errors. So what can we do to be part of the solution?
Yeah, that the man in Detroit that I was talking about, and there are countless others. I could come. I wish I could remember them off the top of my head, but there's countless others. So the Gender Shades Project was probably the first step in really recognizing the issue. MIT did that a couple years ago. The problem is that all of these algorithms are proprietary. Microsoft doesn't tell us how they create this algorithm, or Face++ doesn't tell us. We can run the system. You know, they gave access to MIT to run it, which private companies or police forces pay a lot of money for, but we don't know how they created it. So it's going to be about having some level of transparency in how this stuff is created. But there's much, you know, that would really come under government regulation. You know, saying that there has to be some people, you can't have, you know, capitalist system, you can't also have, you know, you can't have everything be open and transparent, but there needs to be someone regulating it. And I think the key is that until it's regulated, the real way to advocate is to say you don't want it in your community. That's local government. You know, that's saying, that's writing to congressmen, that's, I don't know, however you advocate in local government, that's saying, I don't want this in my community, I don't want this on my streets, because it is, and you have no idea. It's in Los Angeles, Tucson, Arizona, or Phoenix, I can't remember which one has it. I mean, there are reports of cities that actually scan the sidewalks for people for faces with mugshots. Like, it's happening right now. And people will say, oh, well, so there's one group that says for police that use body cams that have facial recognition, and I'm using the example of the police just because it's an easy example. Their body cams sometimes have face recognition. And so people say, well, we'll just put the percentage chance that it's the person. Well, if you're a policeman and it comes up that it's a 65% chance that this is a guy who just murdered a cop yesterday, are you gonna be like, oh, it's only 65%, I shouldn't get really scared? Of course not. You're gonna be terrified. Like, you can't compute that it's only a 65%. What about the other percent? Like, no way. So it's not really a fair thing, I think, to say, well, you should just be able to look at the percentage probability that it's right and make that snap-second decision when you're afraid. Like, it's not fair. You saw how long, I mean, it took you guys a full, 30 seconds in the chat under a no-pressure situation to figure out whether it was the right or the left deep fake. You know, how can you expect someone to understand the probability of a facial recognition system in a split second under really serious circumstances? So I think really the only way to advocate is to say, I don't want this in my community.
Yeah, thank you so much, Liberty. Really fascinating talk. So I have a question for you. So when you mentioned about the Zillow as a tool to predict a housing price, recently I'm noticing that some people actually are using Zillow as a guideline to price their house when they go to the market. So there is some kind of either the balancing loop or reinforcing loop there involved. This is resulting in a convergence of the predicted price and the true price. Could you talk a little bit more about this? Is a phenomenon unique, or you've seen this kind of convergence in other places?
You know, that's a really interesting question, and I wish I could come up with a great example of that, because it's being used, it's reinforcing your own confirmation bias, right? Zillow told me I should sell my house for this much, and that's how much I sold it for, so it's correct. And also then it informs Zillow that it's correct. And you see enormous differences in sort of areas, especially right now with the housing market, in areas where that are really hot. So my parents live down in Florida, and in Naples, Florida, the prices will say a house should sell for $2 million, and people are selling them for $6 million. I mean, it's nuts. But it's because Zillow doesn't, it looks at the square footage, it looks at the listing price, it looks at all these things, and it goes, well, that's what it should be, but everyone on the planet wants to move to Florida right now, and the housing prices are 10 times more. But then you get these random houses that are listed for the actual Zillow price, and it's because people just look at Zillow and they put up the price. And then you'll also see buyers come in and say, well, I'm not going to offer you that amount. I'm not going to offer you $500,000. Zillow told me it's only worth $400,000. So it's 100% confirmation bias. We see something, so therefore we think that's what it must be. So there are tons of examples where confirmation bias comes in. And in the social sciences, I think confirmation bias seems rampant. In the social sciences, you make a hypothesis before and you get the data says whatever it is that you'd like it to say.
Wonderful.
And unfortunately, we are at time. I mean, honestly, Dr. Vittert, with that comment that you just make, I feel like we could go another hour to unpack that, because that is truly the heart of this series, talking about AI applications. Before we end today's program, I just want to give you an opportunity to share any final thought, call to action, or next step that you want to make our audience aware of. What would you like to leave us with?
Well, I just thank you so much for inviting me. And I looked at some of these other open classroom. I mean, this is an incredible forum. So I just hope I will be attending. So I hope more people continue to attend these lectures, because you guys have done an incredible job bringing in such different voices.
Thank you so much. Thank you for being here. And the generous comment, this AI in the Social Sciences series is Rupang's baby. And we will be running monthly events through this academic year. So lots of opportunities to come together and learn more. Well, Dr. Vittert, thank you for being with us. To my colleagues, Rupang and Smriti, thank you so much for your partnership. I really enjoy, and I'm learning a lot. Thank you to our audience, which has been wonderfully participatory. With this, we're going to say goodbye. Wish everybody healthy and safe. Happy New Year. Happy holiday season as it applies. And we'll hope to see you again very soon. Take care, everybody. Bye now.
Thank you so much. Bye, everyone.